Hey guys, welcome back to another round of chemistry notes. This is the last video for Unit 7, and in this video we are going to talk about oxidation reduction reactions. So first, oxidation reduction is too many syllables and too many letters, so we usually shorten it and just call them redox reactions, and that's pretty much what I'm going to call them all throughout the video because scientists are nothing if not efficient. So redox reactions occur when electrons are transferred from one atom to another. Obviously, there are two ends to this. There are the elements that gain electrons and the elements that lose electrons if the electrons are being transferred. The elements that gain electrons are reduced. If you are being reduced, you are gaining electrons. If you are gaining electrons, you're being reduced. It's a little weird to think about because you think of reduce as getting smaller and the number of electrons is getting bigger, but when have electrons ever followed the rules? There is a reason that it's called this. So for right this very second, just take a leap of faith with me. Elements that gain electrons are reduced. They are called sometimes oxidizers or oxidizing agents. We'll talk about that more in just a second. So if you have elements that are gaining electrons, someone else must be giving them up because remember, matter cannot be created or destroyed. We cannot materialize electrons out of nowhere. If one element is gaining them, it's because they came from something. It came from the elements that lose electrons, and the elements that lose electrons are oxidized. And these are called reducers or reducing agents. So your oxidizers are called oxidizers because they cause the other thing to be oxidized. And your reducing agents are reducers because they cause the other thing to be reduced. It's a little weird. We're going to sort of put this all together at the end. Knowing what they are called is less important than knowing that if you are gaining electrons, that is reduction, and if you are losing electrons, that is oxidation. If you have to forget something from this slide, forget this thing. Like ideally you would remember it, but if you got to cut something out, cut that second bullet. Reduction is gain, oxidation is loss. Let me help you remember that. There are two mnemonics for you. You can take your pick, choose your favorite. The first one is oil rig, meaning that oxidation is loss, reduction is gain. And these are talking about of electrons. So that's one. That's my personal favorite. Short, sweet, and to the point. Oxidation is loss, reduction is gain. Oil rig. The other version is Leo goes grr. And that means that atoms lose electrons when oxidized and gain electrons when reduced. So you can imagine a lion. The little kitty nose. He's a mad lion, so he's saying, grr. This is Leo. He's a lion. So either way, whatever you find easier to remember, oil rig, Leo goes grr. In any case, you need to know that if something is losing electrons, it's being oxidized. If it is gaining electrons, it's being reduced. You must know this. So the way we can identify whether electrons are being lost or gained, how they're being transferred, how they are moving, is with something called oxidation numbers. They're also called oxidation states. These two terms, oxidation numbers and oxidation states, these are interchangeable. They mean the exact same thing. So oxidation numbers, oxidation states, they're not real. They're imaginary charges that we assign to each element. There's a very specific system to it, but it's kind of arbitrary because they don't really mean anything by themselves. What we care about is how they change throughout the course of the problem. So we're going to look at how oxidation numbers change. Do they go up? Do they go down? And that's going to tell us whether things are oxidized or reduced. So again, we use them to determine electron flow. Your oxidation state will increase when an element is oxidized, and it will decrease when an element is reduced. So remember, this whole situation where reduction equals gain, and that was a weird thing that we're gaining electrons and calling it reduction. It's called a reduction because it's the oxidation state that's being reduced. It's getting more negative. Versus when you're oxidizing, the oxidation number is increasing. It's getting more positive. And again, if you think about this in terms of the electrons, that theoretically should make sense. If you are gaining electrons and electrons are negative, you are becoming more negative. This is just like forming ions. More electrons, more negative. So it's going to decrease this oxidation state. If you are losing electrons, being oxidized, then you lose electrons, you lose the negative thing, and your oxidation state increases, becomes more positive. If over the course of your reaction, your oxidation state doesn't change, that means it's not a redox reaction. Most reactions are redox. There's sort of one special case that you can count on to never be redox, and besides that, they generally are. Okay, a lot of information, a lot of vocab, a lot of big words. Let's sort of summarize it. So you've got your oxidizing agent and you've got your reducing agent. The oxidizing agent is reduced. It is reduced because it is gaining electrons. And when you gain electrons, you become more negative. Your oxidation number decreases, becomes more negative. On the flip side, you have your reducing agent. It is a reducing agent because it is being oxidized. Oxidation is loss. And if you are losing electrons, then you are becoming more positive and your oxidation number will increase, more positive. This is kind of a confusing thing. If you can get over this hump, you're going to be okay with redox. So if you need to go through, pause the video, and sort of explain this to yourself, that might not be a bad choice. We are going to practice a lot with it, and it should start to click into place a little bit more. So that being said, let's go ahead and see an example with this. So we are eventually going to learn how to assign oxidation numbers all on our own, but for right now, they're given. We're given this reaction of zinc, solid metal zinc, reacting with an iron cation to produce a zinc cation and metal iron. We need to figure out what was oxidized and what was reduced. So remember, oil rig, oxidation is loss, losing electrons. Reduction is gain, gaining electrons. If you're losing electrons, remember that means you are getting more positive. And if you're gaining electrons, that means you're getting more negative. So let's take a look. Zinc, as we go from the left-hand side, and we're always going to be comparing across our yield arrow. So as we go from zinc to the zinc ion, that oxidation state increased from 0 to +2. It became more positive. So we can say that zinc was oxidized. We're always going to be looking at the reactants when we're deciding what was oxidized and reduced. So zinc must have been oxidized because its oxidation state increased, became more positive. Because it was 0 in the reactants and it was +2 in the products. If the oxidation state increases, we must have lost electrons. A loss of electrons is oxidation. So that kind of gives away which one is reduced, but we can still double check it. We are left with the iron ion over here with a 2+ or a +2 oxidation state in the reactants. And in the products, it has a 0. So from here to here, the oxidation state became more negative. So we can say that Fe2+, because again, it should always be a reactant, Fe2+ was reduced. because the oxidation state decreased. It became more negative. It must have gained electrons, and reduction is gain. It's a little weird, this system. Here's a second example. Pause the video, try it on your own, see if you can reason through it, and then when you're ready to check your work, unpause the video and we'll go through it. All right, so the first question is, what was oxidized? Here we've got three elements. We're looking at carbon, hydrogen, oxygen in the reactants, carbon, oxygen, hydrogen, and oxygen again in the products. So let's look at carbon to carbon first. Carbon starts -4, ends +4. That is definitely a change from here to here. That is becoming more positive. More positive means we must have lost electrons. A loss of electrons is oxidation. So we can say that the carbon in methane in CH4 was oxidized. And we know this because the oxidation state increased from -4 to +4. So we still have two options now for what's reduced. Maybe it's hydrogen, maybe it's oxygen. If we look at hydrogen on the left, it is a +1. Hydrogen on the right, still a +1. So whatever's happening here, it does not involve hydrogen. Let's take a look at oxygen. Oxygen starts with a 0 oxidation state, ends with a -2 and a -2. So from here in the reactants over to the products, that is decreasing. It's becoming more negative. Means we must be gaining electrons because electrons are negative. So we must be gaining electrons, and a gain of electrons is a reduction. So for what is reduced, we can say it's the oxygen in the O2. And we know this because the oxidation state decreases from 0 in O2 to -2 in water. All right, hopefully this is starting to make a little bit more sense. If it's not, maybe go back, watch these two examples one more time, stop, explain it to someone, explain it to your parents, and then move on, look at some practice. You have 5 practice problems in your book. Pause the video, work through them, and when you're ready to check your answers, unpause. Hopefully at this point you're doing okay identifying what is redox and what is not, what is oxidized and what is reduced, because now we're gonna back it up a step farther. You, for the most part, will not be given oxidation states in problems. You're gonna have to produce them for yourself. And the end goal is still gonna be to say what was oxidized, what was reduced, but you're gonna have to produce the oxidation states that you're using to do that. So let's go ahead and learn how to assign oxidation numbers. There's a set of rules. It is very important that you follow the rules in order. The rules are given in order of priority, meaning that the first one is the most important and the last one is the least important. So if you have two rules that disagree, follow the rule that's higher on the list. Follow the rule that comes first because that rule is more important. Here we go. Here are your rules. If you are looking at just a single element by itself, it's not in a compound, it's just one element, either an atom or an ion, the oxidation number on that element will be whatever the charge is. So if you have magnesium by itself, just the atom, that has a charge essentially of 0 because we don't see a charge, so it's neutral, the charge is 0, meaning the oxidation number is 0. If you have a magnesium ion, Mg2+, the charge on that is 2+, so the oxidation state is +2. If it's just one element, whatever the charge is the oxidation number. If it's a compound that you're looking at, the oxidation state of every element in that compound should add up to the charge of the compound. So, for example, one of the ions we've learned this year is iodate, IO3, 1 minus. You might not know off the top of your head what the oxidation state of iodine and the oxidation state of oxygen are, but when you add this oxidation state plus these oxidation states of these 3 oxygens, they should add up to -1 because that's the charge, is a -1. So always make things equal the charge. Now, those are sort of your vague general rules. Now we can get into more specific rules. Your group 1 metals, your alkali metals, sodium, potassium, strontium, those metals are always going to have an oxidation state of +1, assuming that doesn't disagree with rule 1 or rule 2. Your group 2A metals, your alkaline earth metals, magnesium, calcium, barium, those are going to have a +2 oxidation state, assuming that doesn't disagree with rule number 3 or rule number 2 or rule number 1. Your non-metals have their own hierarchy. They follow this chart. So fluorine is the most important. You'll assign an oxidation state to fluorine first, and then hydrogen, and then oxygen, and then group 7, 6, and 5. There are many tricks for this, but the bottom line is you have to memorize these rules. You need to know these rules in order. It is kind of a lot to memorize, but you have to know these rules and you have to know them in order, because if you do them in the wrong order, you will eventually start working problems incorrectly. So let's go ahead and practice assigning some oxidation numbers. Our first example is Na+. This follows rule number 1. It's a single element. It's not in a compound, it's just an element all by itself. The charge on this element is a +1, so the oxidation state of this ion must be +1. That's it. That's its oxidation state. Equals the charge. Our second example, not so straightforward. Here we have carbon and we have hydrogen. So we need to figure out which of these two is more important. Neither one is an alkali metal. Neither one is an alkaline earth metal. So then we look at our hierarchy of nonmetals. Hydrogen is right here on the list. Carbon is not on this list. So we're going to look at hydrogen first, and then we'll take care of carbon. Hydrogen likes to have an oxidation state when it gets its choice of +1. Carbon is going to take one for the team here. The last element to get assigned an oxidation state just has to make up the difference. So we're going to do some algebra that probably looks a little familiar to you. We know that hydrogen has an oxidation state of +1. We know that we have one carbon atom. We know that we have one carbon atom, but we do not know its oxidation state. We know that we have 4 hydrogen atoms, and we know that each one of those has an oxidation state of +1. And we know that the charge on this methane is 0. And we know that the charge on this compound is 0. So when we add up all of our oxidation states, they need to equal 0. So now we can do some algebra. 1 times x is x, plus 4 times 1 is 4 is equal to 0. X is equal to -4. So the oxidation state on carbon is going to be -4. And we can show this by just doing -4, and then a comma, and then +1. And that shows that our first element has a -4 state, and our second element has a +1 state. And if we take this -4, add it to these 4 positives, that'll give us the 0 that we needed. Let's look at another one. Next example is ammonium NH4+. So again, no metals, all nonmetals. Your order of nonmetals goes fluorine, and then hydrogen, and then oxygen, and then group 7, then group 7, 6, and then 5. So this is nitrogen down here, and this is hydrogen up here. We're going to assign an oxidation state to hydrogen first, and hydrogen likes to be +1. So that's what it's going to be. So now we'll do the same thing we did a second ago. We'll say hydrogen is going to be +1, and then we'll do some algebra. We have 1 nitrogen. We do not know its oxidation state. Plus, we have 4 hydrogens. They each have an oxidation state of +1. Here's how this is different from our last problem. Now the charge on this compound is a +1. So these are not going to add up to 0. These are going to add up to +1. And then we'll solve the same way we did a second ago. X plus 4 equals +1. Subtract 4 from both sides. X is equal to -3. So that means the oxidation state on our nitrogen is a -3. So we can write that as -3, +1. All right, halfway through with these examples, take a second, pause the video, work through the next 3 on your own, and then unpause the video to walk through it with me. All right, number 4 is a really pretty one. This is your ion dichromate that you will be asked to memorize in the 5th 6 weeks. We're going to follow our same steps. Here we have a metal, but it's not an alkali metal. It's not group 1A. It's not an earth metal. It's not group 2A. And those are the only 2 groups of metals that really matter. So now we go looking at our nonmetals, and we'll come back to chromium. So remember, your order of nonmetals is fluorine, and then hydrogen, and then oxygen, and then group 7, 6, and 5. Well, here's oxygen right here. Oxygen likes to have a -2 oxidation state. So we'll say oxygen's going to be -2. And then we'll do the same math we've been doing. Oxygen will be -2. We have 2 chromium atoms. We don't know what their oxidation state is. We also have 7 oxygen atoms. Each of those has an oxidation state of -2. When we add these all together, we should get the charge of this ion, which is a -2. And now we'll do some math. 2x minus 14 is equal to -2. Add 14 to both sides. We get 2x is equal to 12. Dividing by 2 on both sides, we will get x is equal to 6, specifically +6. So that's going to be our oxidation state for chromium here is a +6. So we have +6, -2. To be clear, this is the answer. This is all scratch work. If you're asked to find the oxidation states, this is all that matters. All right, your next one, number 5. This is an easy one. It's an element all by itself, so the oxidation state is just the charge. But this is neutral. It has a charge of 0, so the oxidation state is 0. And that's it. Last but not least, we have our sulfite ion. Here again, we have 2 nonmetals. Remember your order, FHO 765. Well, this is oxygen right here. And then sulfur falls into this category right here. So oxygen wins. It will go first. Oxygen likes to be a -2. So we'll give that a -2. And then we'll do our math. We have 1 sulfur. We don't know what its oxidation state is. We are going to add that to our 3 oxygens that each have a -2 oxidation state. When we add this all together, it should equal the -2 charge that every sulfite ion has. So then we have x minus 6 is equal to -2. Adding 6 to both sides, we get X is equal to 4. So the oxidation state on sulfur is a positive 4. And again, this is why it's important to do these in order, because if we had done this the other way around, we would have gotten a completely different answer. Sulfur would have been -2, and oxygen would have been something truly bizarre. So make sure you are following your list of rules. 1A, 2A, fluorine, hydrogen, oxygen, group 7, group 6, group 5. This is your hierarchy of needs here. All right, next in your book, you've got some practice. First, it's practice just assigning oxidation states. Then it's practice assigning oxidation states and using them, putting it all together, applying it with what we just did a minute ago. So go ahead, work through all this practice. When you're ready to check your answers, unpause the video. All right, I've got the keys up on 2 slides here, since there's sort of a lot of practice problems. Here are your first 10 answers with just finding oxidation states, and then for applying oxidation states. If you are looking at this and thinking, that is not what I got, you can head over to my website to look at the actual key where I show what I had for my oxidation numbers. Maybe something went wrong in finding your oxidation states. Maybe you forgot that reduction is gain of electrons, more negative, and oxidation is loss of electrons, more positive. Remember, you got to squish all of that together. All right, this is it for Unit 7. This is the last new thing we're going to learn. So at this point, you should go back, troubleshoot any problems you're having, look over old videos if you need to, or move on and start preparing for your test. As always, make sure to come in for tutorials if you're having trouble. Good luck and happy studying.